Hey guys, so this is going to be our first online video lecture, or whatever you want to call it. We are going to kick this series off with Chapter 5, specifically Section 5.1, which is going to be on the antiderivative. So consider this situation. Suppose we've been given some kind of velocity function and it's in this form. V of t is equal to 3t squared plus 2t. But we want to find the position function s of t. How can we get this function? So usually the way this works is we're given a position function and we want to find the velocity function. But now it's the other way around. We have a velocity function, but we want to work back up, so to speak, to get our position function. So that's what we're going to explore on how to do. Well, first thing, it's important to remember the relationship between the position function and the velocity function. The velocity function is simply the derivative with respect to time of the position function. Remember, velocity and position are both functions of time. So when we take our derivative, taking it with respect to, say, x would be kind of pointless. We have to take the derivative with respect to the appropriate variable. So we have v of t is equal to the derivative of s of t. And if we examine the velocity function, 3t squared plus 2t, we can kind of see that 3t squared is actually just the derivative of t cubed. Because when you take the derivative of t cubed, use the power rule, pull down the exponent, subtract 1, you get 3t squared. So 3t squared appears to be the derivative of t cubed. And if we look at 2 times t, well, that just looks like the derivative of t squared. So by using that kind of intuition, we can actually kind of work backwards and build this. We can kind of conclude that the position function looks something like t cubed plus t squared plus or minus some constant. If you don't believe that, what you can do is double check. Take the derivative of this function t cubed plus t squared. When you do, you get 3t squared plus 2t, which is exactly our velocity function. So this is a good candidate for our position function. Now, that required a little bit of intuition, didn't it? We had to look at these two pieces and try and recognize what we took the derivative of to get there. That seems kind of hard to just kind of eyeball and look at. So it leads to the next question. Is there a way we can formalize or make strict this technique or this process? Is there a way that we can make this formal? Well, this leads us into the concept of antidifferentiation. Now, a little bit of terminology here. So, because there's going to be a lot of F's flying around here, I'm going to talk about capital F and lowercase f, all right? So, I'm going to try and be as clear as I can on which F I'm referencing. So, capital F is an antiderivative for little f if the derivative of capital F is equal to little f. Now, that was a lot of F's. Kind of weird. So, a way to think about this is if we have some function f and its derivative is little f, then what we say is big F is the antiderivative of f. So f, little f, is the derivative of capital F. Then capital F is the antiderivative of f. Think inverse functions, so to speak. They're not inverses of each other, but think of that kind of a process of undoing each other. One is the derivative of the other, which makes the other the antiderivative. Don't worry, we're going to spend a lot of time dealing with this. So you'll get comfortable with the terminology pretty quickly. Now, we have that. We also call f, capital F, the indefinite integral of lowercase f. So this is our first introduction of what we call the integral. So capital F is called the indefinite integral of lowercase f. That is a lot to say. It's kind of frustrating to say that all the time. So now we're going to introduce some notation to denote this indefinite integral. It looks like this. The notation we're going to use is the integral of little f of x dx. And how we would say this out loud is this is the integral of f of x dx. So let's look at this notation real quick. So we have that elongated s looking thing. That's what we call the integral. Then we have our function f of x. The reason I put the of x part is to specify that this function is a function in terms of x, and then see that little dx after it. Well, the reason we have that is because that's telling us what variable we are integrating with respect to. Think back to the derivative. We had the function of what we're taking the derivative with respect to, the dx. And in the integral, we have that same notation, that little dx, to denote what variable we are integrating with respect to. All right, we're going to go into a lot more detail about that. So right now, this is just a basic introduction to the notation. Right now, just note, this is the operator. This is what we're doing when we're taking the integral. We're going to go into more detail about what exactly that dx is later. All right. So next we want to talk about is, what is antidifferentiation? What's a way to think about it? Well, a way to think about it is undoing the derivative. So we have some function that we think is the derivative of something else, and we want to find what that original function was, the antiderivative. And then what we're going to do is integrate it, or take the integral of that function. We are essentially undoing the derivative. Okay, now let's look at an example, because right now just looking at all these new symbols and big F's and little f's has just got to be confusing. So let's look at a hardcore example. Consider the situation. Little f of x is equal to 2x, and capital F of x is equal to x squared. So we can just kind of look at that and kind of deduce that x squared is the antiderivative of 2x. Don't believe me? Take the derivative of x squared. When you take the derivative of x squared, you get 2x. So big F is the antiderivative to little f. All right. But isn't x squared plus 2 also an antiderivative of little f? Take the derivative of x squared plus 2. You again get 2x because the constant disappears. We repeat that process. What about x squared plus 7? X squared plus 42. These are all antiderivatives for little f. As a quick exercise, take a second real quick and differentiate all three of those capital F's. And confirm that you actually end up with 2x. So all of these capital F's are antiderivatives. They all do the job. So what that tells us is the antiderivative is not actually unique. So that's something you really need to keep in mind. The antiderivative is not necessarily unique. We may have a couple capital F functions that do the exact same job. All right. Now, when we come upon a differentiated function, so we're given a function and we know that it is the derivative of another function, then we can actually go find that original function. We can rebuild it. We can recover it, except for the constant. Look back at this. When you have x squared plus 2, x squared plus 7, x squared plus 42, that constant can be anything. We do not know what it is. So we can only recreate the antiderivative up to but not including the constant. So we want a way where we can write that down, where we can express that we have the antiderivative, but we have all of the antiderivatives. So we can get all of the terms of x correct. We can get that spot on. The problem is the constant. So by using the before notation to describe little f and big F together, we can write this. The integral of 2x with respect to x is equal to x squared plus c, where c is any constant. It is any real number. That includes 0. If it's 0, it doesn't matter. X squared is still an antiderivative to 2x. So this is how we would write this down. The integral of 2x dx is equal to x squared plus some constant c. All right? So when you're taking this integral, when you're taking the indefinite integral, do not forget that constant. That constant is very important, because if you leave off the constant, what you're saying is is this function without the constant is the only antiderivative. It must be equal to this. But that's not necessarily true. It needs to have that constant in there. Now, when I learned about antiderivatives a lot longer ago than I'm going to tell you guys, my professor had an interesting way for us to remember that C. He called it the houseboat. Now, if you're wondering what on earth an integrating constant has to do with a houseboat, well, that's the point. It makes absolutely no sense. It's bonkers. It's dumb. It has nothing to do with integration, but that's what makes it stick in your head. So if you ever hear me say the phrase, don't forget your houseboat, what I'm really saying is do not forget that integrating constant. It is very important that you guys remember this constant, because by ignoring the constant, you're saying is I have the only antiderivative, which is not true. There is uncountably many antiderivatives. But by putting this plus C, you're acknowledging that there could be a constant there, which is basically a cover your butt tactic. That means I'm covering all the bases. I have all the antiderivatives in my hand right now. All right. Now let's look at some properties of the integral. So these are very important properties that you need to know. These are just properties that you have to have memorized off the top of your head. So let's look at the first one. This is the constant rule. So we have the integral of some constant times f of x dx. Well, that's just equal to the constant times the integral f of x dx. In other words, we can pull the constant out in front. Remember, we're undoing the derivative, so in some regards, we get similar properties to the derivative. When you take the derivative of a function times a constant, we can pull the constant out in front. We can do the exact same thing here with the integral. You know how, like I always say when we're doing example problems, when you're dealing with constants, just pull it out in front and tack it on at the end? The integral allows us to do that as well. It's a very handy technique and trick. Now, let's look at the next one. Here, we have the integral of the sum of two functions, f of x plus g of x, is in fact equal to the integral of f of x dx plus the integral of g of x dx. Another way to put this is the integral of the sum of two functions is the integral of the sums. You can break it up. So the integral of the sum is the sum of the integrals. That's the way I meant to say it a second ago, but I'm a little far in this video and we're committed. So the integral of the sum is the sum of the integrals. And by combining this rule with the constant rule, we can actually change this a little. We can actually make this a subtraction as well. So the integral of the difference of two functions is just the difference in the integrals. When you have plus or minus, we can just pass the integral to both terms, just like we can with the derivative. If you want to take the derivative of a polynomial, we just take the derivative of each term individually. Makes things a whole lot easier. We can do the exact same thing with integrals. Now, I would like to point out real quick that just like the derivative, we cannot do this with products and quotients. We have to do other things. We do not have the machinery to handle those yet. But just like in the derivative, how when you have the derivative of two functions times each other, you have to use the product rule. You cannot just take the derivative of each function and multiply it together. We can't do that. That's why we have the product rule and the quotient rule. And since the integral is just undoing the derivative, it makes sense. We can't just pass the integral through multiplication and division. But don't worry about that. Not yet. We're going to go in much more detail on that later. When we get to much harder examples in section 5.5, we're going to hit that in a lot more detail. All right. Now that we have some properties, now let's go on to some rules. Kind of like we had properties of the derivatives or properties of limits, then we have rules, basically ways we can use this to compute things. Because right now, all we've done is look at some basic theory for this stuff. We haven't really learned how we can actually go about computing antiderivatives. Well, if you notice a trend here with all the rules and stuff we've been doing, the first up to bat is the power rule. Yeah, there's like 17 power rules in calculus. You just got to remember the constant or the situation in which we're doing the power rule. This is the power rule of integration. So let's see what this is. What this is saying is it's the integral of sum of x to some power n with respect to x is equal to x to the n plus 1 divided by n plus 1 plus c. So this is a formula you just got to know. You just got to know this off the top of your head. The integral of x to some power of n is equal to x raised to that power of n plus 1 divided by n plus 1 plus your houseboat or your integrating constant. Can't forget that plus c. Now, when we come up with these new rules, you might look at this and go, how on earth are those two things related? How are they equal to each other? Well, the most obvious way we can go about showing it is proving it. Now, I know I said I'm not going to require a whole lot of proofs from you guys. I only like doing proofs that I think are going to be beneficial for you. This is a proof I think is very beneficial, and it is a proof you should be able to do. In any situation where we're given some integrating rule, like this power rule, for example, the best way to prove it is to take the derivative of the right-hand side. Remember, what we're saying here is x to the n plus 1 divided by n plus 1 plus c is the antiderivative of x to the n. Or in other words, what we're saying is the derivative of x to the n plus 1 divided by n plus 1 plus c. When we take its derivative, it's just equal to xn. So if we take the derivative of the right-hand side and we get x to the n, we have shown our result. Because we got to remember the relationship between these two objects. X to the n is the derivative of x to the n plus 1 divided by n plus 1 plus c, or x to the n plus 1 divided by n plus 1 plus c is the antiderivative of x to the n. So let's go prove this rule. Well, as I said, we need to take the derivative of the right-hand side. And when we do that, now we have to use the power rule for differentiation. It's almost like we got this name power rule for a reason. So we take this derivative. Well, we pass the derivative to both terms because the derivative behaves nicely in that regard. So we get the derivative with respect to x of x to the n plus 1 divided by n plus 1 plus the derivative with respect to x times c. Now, on that left side, we're going to do the power rule. On the right, the derivative of a constant. And so we get this. We get the derivative of 1 over n plus 1 to the x to the n plus 1 because the derivative of constant is what? I'm be kind of disappointed if you didn't say 0. It should be 0. Derivative of constant is 0. Just one of those things. Now, we just have to deal with this one last term, and we want to use the power rule. What is the power rule for differentiation? Pull it down, subtract 1 from the exponent, and you get something that looks like this. We pull down that n plus 1 because while n plus 1 looks weird, n plus 1 is just a number. That's it. It's just a number. So we can pull it down. So we have n plus 1 divided by n plus 1 times x to the n plus 1. But since it's the derivative power rule, we need to subtract 1 from the exponent, and we're left with x to the n. This is another example as to why we have to include that constant, because when we take the derivative, that constant goes away. There's really no way to determine what that constant is without additional information. There's really no other way. And with the information we are given, we just know it is a constant. We don't know anything else. And what we've done here is that we have proven that the derivative of x to the n plus 1 divided by n plus 1 plus c is equal to x to the n, which means that the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus c. Now that might be the 19th time I've said that right-hand side. It's almost like I'm trying to reinforce what this is. This is one of those rules you just gotta know. It should be off the top of your head. It'll save you a lot of time and misery, I promise you that. We gotta know the power rule. Now, there's one other thing that I haven't really mentioned on this slide that now we need to talk about. I have not really mentioned why at the top here we excluded the case where n is equal to negative 1. So we do not have the integral of x to the negative 1. Take a second and think, if I had n is equal to negative 1, what about this would break? Well, take negative 1, plug it into the right-hand side. You get x to the negative 1 plus 1 over negative 1 plus 1 plus c. What's negative 1 plus 1? Last time I checked, it was 0. But that would mean we'd have a division by 0. And as everybody in this class should know by now, we cannot divide by 0. So this rule breaks when n is equal to -1. So when we're doing the power rule of integration, we have to exclude the case n is equal to -1. So that is why we excluded n is equal to -1. We can't divide by 0. It's that simple. But when n is equal to -1, there has to be something we can do. We can't just leave that case out. If n is equal to -1, that's like saying we do not have an integral of 1 over x. That's ridiculous. If you thought that, then you get a little ahead of me, because the next rule we want to introduce is the log rule. This is why we call it the log rule. The integral of x to the -1 dx, which is the same thing as the integral of 1 over x dx. Because remember, negative exponent means you take the reciprocal. So the integral of x to the -1 is equal to the integral of 1 over x dx, but that's just equal to the natural log of the absolute value of x plus c. Now let's stop and look at that. Remember, the natural log is that logarithm with that exponential base e. Remember that number e? It's like 2.718, et cetera, et cetera, et cetera. It's that irrational transcendental number. It's like pi, but personally I think cooler. But that's a different tangent for another day. So that's what the natural log is, and it's of the absolute value of x. Now let's take a second and think. Why did we take the time to include that absolute value of x? That's not an accident. We did that on purpose. We did that on purpose. Why? Take 2 seconds and think about it. All right. So the natural log of the absolute value of x. We have to have those absolute values because we have to think about the domain of the natural log. What is the natural log of -1? What's the natural log of -17? What's the natural log of -42? These should be very confusing questions because the domain of the natural log is only the positive real numbers. The natural log does not exist for negative numbers. That's why we have to have that absolute value, because if we cannot have x equal to -2 in this situation, it has to be a positive number. Hence, we have to have the absolute values of x. And then we got our little houseboat there. Remember, the domain of the natural log is the positive numbers. So when we take the antiderivative of x to the -1, or the indefinite integral of x to the -1, it's equal to the natural log of the absolute value of x plus the integrating constant. Please do not forget those absolute values. They are very, very important. Without them, this could break. So we have to include the absolute values. And once again, a good way to see this is by doing the proof. So what we're claiming here is that the natural log of the absolute value of x is the antiderivative of x to the -1, or 1 over x. Let's show that. To do that, let's take the derivative of the natural log of the absolute value of x plus c. But that is the exact same thing as the derivative of the natural log of the absolute value of x, because that constant is just going to disappear when we take the derivative. But what is the derivative of the absolute value of x when we take the natural log of it? Well, that's just 1 over x. But 1 over x is equal to x to the -1, and we have proven our result. Natural value of the absolute value of x. Wow, I butchered that impressively. That was weird. The natural log of the absolute value. What is the natural absolute? That's weird. Or did I say natural value? That's even weirder. But the natural log of the absolute value of x plus c is the antiderivative of x is equal to -1. Now, these two rules, the log rule and the power rule, you just need to know these rules. You need to commit them to memory. You need to practice with them. Write them down each 30 times. Put on Family Guy on Netflix or something, and then just write these rules out for an hour. Commit them to long-term memory. Short-term memory is going to be useful for homework. It's not going to help you for the exam or Cal 2 or Cal 3. Chapter 5 is all about integration. This stuff is going to show up in Cal 2 and Cal 3. And I don't mean in a little bit. I'm talking day 1. day one of Cal 2, it's going to be integrals. And they're not going to spend much time reviewing this. They're going to expect you to know it. That's why we're going to spend 2 full weeks on integration and on just integration. So these rules, you got to hammer them down. You got to have them memorized. You got to know them. Now, let's look at this in a little more general setting. In general, if you want to find an antiderivative, you need to undo the derivative. So we're just going to kind of suppose that the function you've been given is the derivative of something else. Well, we need to figure out how to undo that. When you come up with your answer and you think it's right, there's a very simple way to check to see your answer is correct. To check it, just differentiate your answer and make sure you ended up where you started. Think back to the proofs of the log rule and the power rule. How did we prove them? Well, we took the derivative of the antiderivative and made sure we ended up where we started. That's always a way to check your integral, always. If you come up with an answer, take the derivative of it. If you don't end up where you started, well, then either you took the integral wrong or you took the derivative wrong. And since we've been dealing with the derivative for the better part of a month, month and a half now, I'd put my money on that your derivative is correct, and you probably need to recheck what you did with your integral. So that is how you're going to check it. And here's where I'm going to stop part 1 of this video. We have rocked out the theory of this. The next part, well, we're just going to hit you with a bunch of examples, because that's the only way to get good at integration. Practice. Practice, practice, practice. All right. Hopefully I'll see you here in a second with the second part of the video.